So in addition to the matrix function, there is also the cbind function. This stands for column binding. And it's a very helpful, very interesting function because say you have vectors such as 1 and 4. And here, let me draw vectors in a vertical direction. I haven't done that so far. Again, it doesn't really matter in terms of vectors if you graphically picture them as horizontal contiguous cells or vertical contiguous cells. R doesn't really matter in terms of how you picture things. Here for the illustration, let's say you have these 3 vectors. And let's say we have this in X, we have this in Y, we have this guy in a Z vector. So what you could do in order to put them together like this, I'm drawing this sketch just to depict the idea of the output matrix. What you could do is call cbind. Again, assuming that you already created X, Y, and Z, then what you need to put inside is X, Y, Z, and R will column bind all of these guys. So the resulting matrix will be just the whole thing. Here again, I'm going to show you the picture of what that output matrix will look like. Another option to create matrices is with the sibling function rbind. This, as you can imagine, stands for row binding in contrast to column binding. And the idea would be similar. So pretend you have a vector A, and this vector, let's say it already contains 3 elements, 1, 2, and 3. And also pretend you already have a vector B with also 3 elements, 4, 5, and 6. Well, if you want to stack them, if you want to bind them by rows, then all you have to do is call rbind, pass A and B. And what R will do, again, as you can imagine, is it's going to create an output matrix with the elements bound by rows such like this. When using column binding and when using row binding, again, depending on which function you decide to use, be careful because the dimensions or the lengths of the input objects, they have to match either. If you want to put them together by column, the corresponding number of columns or the corresponding length of the input objects, they have to match so that you don't end up with, let's say, here's not the case, but pretend that C had 3 elements, then this column would have 3 things versus X and Y that would only have 2. So just be careful. Same idea applies with row binding. The input objects, they could be vectors or they could be other matrices. The number of rows have to match so that R knows how to row binding them. So let's go back to the idea of atomicity in matrices. And I just told you that matrices are also atomic objects. One reason is because if you take an input vector, well, that vector is already atomic. Let's say we decide to column bind 2 vectors of different types. So let's say we decide to pass a generic numeric sequence from 1 to 5. And let's say we decide to bind this with a vector, character vector, containing 5 elements based on an existing vector in R called letter. So this vector comes already in R. It contains all lowercase letters in the English alphabet. And let's say we want to bind this with 1 to 5. So 1 to 5, this is going to be an integer. The first 5 letters, lowercase letters in the English alphabet, this is going to be character. So I'm mixing 2 different data types. This is where R will apply its implicit coercion rules. So if we mix integers with characters, characters will dominate. So the output of this command will be a character matrix because R is applying its implicit coercion rules. Another characteristic of matrices similar to vectors is that the same principles of vectorization and recycling also apply to matrices. So let's go over a couple of examples. Let's say I want to create a matrix mat using the matrix function, passing a numeric sequence from 1 to 10, and I'm just going to specify the number of rows equals to 5. It will give us a matrix with 5 rows, 2 columns, organizing things again by column measure. So the first column will be 1, 2, 3, 4, 5. The second column will be 6, 7, 8, 9, and 10. So this is our matrix mat. It has 5 rows, 2 columns. Remember, here I just specify the number of rows. R will fill in the blank for the number of columns. So internally, it will calculate the value necessary such that 5 times 2 matches the length of the input vector. So vectorization, I could use functions that are designed initially for vectors, but also for matrices, such as the sqrt function, square root, and pass the matrix input. I could also calculate the logarithms of all these guys. Similar idea, you just invoke the logarithm function, log, log, pass the input matrix. We could also, let's say, calculate the sine or the cosine or any trigonometric function, pass the input matrix, and R will apply the typical vectorized behavior to all these 3 cases. Another example of vectorized or vectorization code in R with matrices, I could take my matrix mat and do something like this, mat plus 1. So in pictures, what are we doing? So in pictures, this command, mat plus 1, can be represented like this. So in this case, R will recycle the number 1 and then apply vectorization to give us the corresponding output matrix. It's going to have the same dimensions of mat, 5 rows, 2 columns, and then just adding 1 to every cell. So you're going to have 2, 3, 4, 5, 6 in the first column, 7, 8, 9, 10, 11 in the second column. Another example, say we take our matrix mat and then we decide to add a vector containing 2 elements, 0 and 1. We have our matrix mat 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then again, it doesn't really matter if you write a vector either vertically or horizontally oriented. Let me write it vertically oriented because internally I told you, especially for matrices, things are going to be stored column major. So what R will do, again, it's going to recycle the elements of the shorted vector. So what you will have here is, I'm not going to write again all the elements in mat. So let me just indicate that this is supposed to be mat with 5 rows, 2 columns. Let's focus instead of how R will recycle the elements in the shorter vector. Again, internally, this is what R will do conceptually. It's going to recycle 0, 1 as many times as necessary in order to match the length or the dimensions, in this case, of the input matrix 5 times 2. So this is also 5 times 2. And then the resulting matrix will be, same idea, 5 rows, 2 columns. And then the inputs will be 1, 3, 3, 5, 5, and then 7, 7, 9, 9, and then last 11. Another example, basic idea, again, you could take your matrix mat and then, for instance, multiply this times 2. Here, I'm just going to go directly show you what the output will be. The idea is that R will vectorize the multiplication and multiply all elements of mat times 2. So the output matrix will be 2, 4, 6, 8, 10 on the first column, and then 12, 14, 16, 18, 20 in the second column.